Hi folks, welcome to the Key Concepts Review for Math 521B, Pre-Calculus 11. We're looking at Chapter 7, which is absolute value and reciprocal functions. Here we're going to solve some absolute value equations graphically and algebraically, and then learn how to graph reciprocal functions. Standard disclaimers apply, and as always you can check the video description below for a downloadable copy of the notes. Solving absolute value equations graphically is pretty simple. All we do is look for x values of intersections. So if I want to solve absolute value of x plus 2 equals 3 graphically, let's see. I know how to graph each one of these. So if I graph this side and graph this side, so I'll have y equals absolute value of x plus 2. Recall from the last video, that means that we're going to graph the basic one, and then we're going to flip any pieces that were below the x-axis above the x-axis. So you can see there's no problem here, but starting right here, the point -3, -1 should become -3, +1. -4, -2 should go up here, and so on. So I get this V shape. Now I'm asked to graph y equals 3. Well, that's a horizontal line at 3. And you can see where they intersect. They intersect right here at x equals 1 and right here at x equals -5. Now, if we're not sure, we can sub that into the original equation. Check x equals -5. Let's see. On the left side, we'd have the absolute value of -5 plus 2. And we're wondering, is that equal to 3? Well, that would be the absolute value of -3. Yes, this works. If I put in 1, well, clearly 1 plus 2 is 3. Absolute value of 3 is 3. Yes, that works as well. Okay, so we can check them. And we probably should check our graphical solutions if we have the equation. If it's just a picture, well, you'll just have to trust your sketch. Solving absolute value equations algebraically is pretty easy. As long as we can produce accurate graphs, we could do it graphically, but that's difficult sometimes and time-consuming. So when you remove absolute value brackets, there are only two possibilities. Either the absolute value brackets did something or they didn't. So if I have absolute value of some function equals k, some constant, there are only two possibilities. Either f of x equals k, meaning the absolute value function brackets did nothing to that function. It was already positive. Or they did something, in which case the actual function was the negative of what you want, and the absolute value brackets turned it positive. That idea is going to let us solve without producing graphs. So I'll show you what I mean in this one. We should always check our answers, though, for absolute value. So this has two possibilities. Absolute value of x plus 2 equals 3. We're saying it's either x plus 2 equals +3, or x plus 2 might have equaled -3. In which case the absolute value bracket did something. Let's solve each of these. This is going to be x equals 1. This one will be x equals -5. You might notice this is the exact same example we just did, and those answers worked out. But again, let's check them. So if I check x equals 1, I'm saying, is the absolute value of 1 plus 2 really equal to 3? Is the absolute value of 3 3? Yes, it is. This is a solution. Okay? So I can circle it. Let's check x equals -5. So is the absolute value of -5 plus 2 equal to 3? Meaning, is the absolute value of -3 equal to 3? Yes, it is. X minus 5 is a solution. But it's possible that you'll have extraneous roots, ones that don't work at the end. We'll work this through in a couple of other examples. So this first one, we have absolute value of x minus 4 equals 2x plus 1. So remember, the technique here is either the absolute value signs did nothing, or they did something. X minus 4 equals, you have to negativify this whole side. Change the signs on it. Okay, now we're just going to solve, so I'll move over a 1, and I'll move over an x. That's going to give me x equals negative 5. For the other one, maybe I'll move the negative 2x over. That gives me 3x on the left, and I'll get positive 3 on the right, so x equals 1. Coincidence that we have the same answer? Let's make sure that they actually work. So check, x equals negative 5. So absolute value of negative 5 minus 4. Is that equal to 2 times negative 5 plus 1? In other words, is the absolute value of negative 9 negative 9? No, it is not. The absolute value can never be a negative number. So this is one of those extraneous roots we were talking about. It doesn't work. And because we found one of those extraneous roots, does not guarantee that they're not both extraneous. So we need to check both. Check x equals 1. Hopefully this one will work. This will be absolute value of 1 minus 4. And we're wondering, is that equal to 2 times 1 plus 1? Or is the absolute value of negative 3 equal to 3? Yes, it is. This is a solution, and it's the only solution. Taking a look at b, something like b is a bit of a gift. So we could go through the process. We could say 7x plus 3 is negative 4, or 7x plus 3 is positive 4. We could solve each of those. This is going to give us x equals negative 1. The other one's going to give us positive 1/7. We could check them, and they'll both fail. But you actually knew from the very start that they were going to fail. The equation said the absolute value of something is a negative number. That's never going to happen. If you have absolute values of something equal to a negative constant, no solution. So if neither of them work, we say no solution. You could do that by going through the entire problem or just by inspection at the beginning. Some of the longest, but not necessarily most difficult questions are the absolute value quadratic equations. So here I've got absolute value of x squared minus 2x plus 2 equals 3x minus 4. The process is just the same here, though. Either the absolute value signs did nothing, or they did something. Each of these are quadratics that need to be solved. So this will give us minus 5x plus 6. Okay, that factors to x minus 3, x minus 2. We're masters of factoring at this point. So x might be 3, or x might be 2. These are all just candidates. Let's try the other one. We'll have plus x minus 2. That'll give us x plus 2 and x minus 1 when we factor. Or potential solutions of x equals negative 2 or x equals 1. All of these need to be checked, but it doesn't need to be a long process. So, the absolute value of 3 squared minus 2 times 3 plus 2, is that equal? I'm checking x equals 3 here. Is that equal to 3 times 3 minus 4? Let's see, what would I get in here? I would have the absolute value of 9 minus 6 plus 2. That's absolute value of 5. Is that equal to 5? Yes, it is. Ding, ding, ding. We have a solution. Okay, let's check x equals 2. And these checks can go pretty quickly. So that's going to be 2 squared. I'm just using the original equation. Has to go into the very original one with the absolute value signs. Minus 2 times 2 plus 2. Is that the same as 3 times 2 minus 4? Okay, that's going to be the absolute value of 2. Is that equal to 2? Yes, it is. Again, we found a solution. So this one is an answer. Let's check our other ones. Check x equals negative 2. That's going to be absolute value of negative 2 squared minus 2 by negative 2 plus 2. And we're wondering, is that the same as 3 times negative 2 minus 4? So the absolute value of 4 plus 4 plus 2, so that's absolute value of 10. And on this side, we'd have negative 10. Clearly, that's not going to be true. So this does not work. It fails. Let's try the last one. X equals 1. That's going to give us 3 times 1 minus 4. Now you might see right away on the right it's going to be a negative number, so it won't work out. Well, that's okay. We'll just make sure by showing all the steps. So absolute value of 1, is that equal to negative 1? No, it is not. So our only solutions are 2 and 3. Now I will mention that there are alternate approaches for solving absolute value equations, knowing the zeros of the absolute value portion and setting domains for each case. And your textbook does go through that. But it requires you to have a really, really good idea of what each of these graphs look like. And I find hunting each potential solution and then checking goes faster. And there's sort of less upfront work to do. You just set your two conditions, you solve, and then you check them. Okay, lastly, we'll look at reciprocal functions. So if I wanted to compare the graph of y equals x squared minus 4, and it's reciprocal, y equals 1 over x squared minus 4. Let's see what happens. If I can get the smartboard to cooperate. Here we go. Oh, wow. That looks strange. Now let's see what's happening on the red one. On the red one, there seems to be a vertical asymptote here and a vertical asymptote here. An asymptote is a line that the graph gets infinitely close to but doesn't touch. There are a couple of other features. Wherever y is 1 or negative 1, the purple and the red graphs intersect, meaning that they don't change their y value. And I suppose the last thing to notice is wherever the purple graph is big, the red graph is small. And whenever the purple graph is small, the original is small, its reciprocal is big. And that makes sense. If you had, say, a y value of 10, the reciprocal is 1/10, very small. So the things we want to notice here when we compare y equals f of x and 1 over f of x. X-intercepts on f of x are undefined on the reciprocal and therefore become vertical asymptotes. So check out where those vertical asymptotes happened. They happened where you had x-intercepts on the purple one. Big values on f of x are small on the reciprocal. So here's a place where there's big value on f of x, it's small on the reciprocal. Small values on f of x are big on the reciprocal. Okay, so here's where we had small value on the purple, made for a big value on the red. Y values of 1 and negative 1 are invariant. That means they don't change. And every point xy maps to x 1 over y on the reciprocal. That means just flip the y coordinates. as in take their reciprocal. That is not the same as reflecting them. We reflected for absolute value, so pop stuff that was below the x-axis above it. Here we're just taking the reciprocal of every y-coordinate. So let's take that idea and sketch a reciprocal. Whenever you see x-intercepts, those are going to become vertical asymptotes. And vertical asymptotes always take the form x equals something. So this is a vertical asymptote of x equals 1 and a vertical asymptote of x equals 5. We also said that the graphs are going to be invariant when y is 1 or -1. So all those points are going to be on the reciprocal graph. I have a really important point here of 3, -4. On the reciprocal, that is going to become the point 3, -1/4. I just flipped the y value. And I could do that for a whole host of other points. So this point right here could become 4, 1/3. I'll just eyeball that. This one right here would become 2, -1/3. The last thing we might notice is that big values on the original become small values on the reciprocal. Big value here makes for a small x value. And similarly, small values on the original make for big values on the reciprocal. And this was a small positive value on the original right here, so it's going to be a big positive value on the reciprocal. Now we just connect. So I have to go through that invariant point, and I have a vertical asymptote. Here I have a vertical asymptote. I need to go through the invariant point and some of those other ones that I marked. And on the other side, I've got a big value I start with. Go through that invariant point, and things get smaller and smaller. For a polynomial, if it gets bigger and bigger on the original, then the reciprocal will get smaller and smaller, meaning you'll have a horizontal asymptote. Let's do one where we're not given the original. So we're going to graph x minus 2 and 1 over x minus 2. X minus 2 looks like this. It's got a slope of 1. There we go. When I go to graph the original, there's an x-intercept right here, so that's going to be a vertical asymptote. This point is invariant. This point is invariant. There are no vertices, but I know right here I've got a small positive value on the original, which makes for a big positive value on the reciprocal. Right here I've got a big positive value on the original, so its flip is going to be small. That must be that portion of the graph. On the other side, right here, I have a very small negative value, so its reciprocal is going to have a big negative. Right here, I have a big negative. Its reciprocal will be a small negative. And now I can go and smoothly connect. And as we go far to the right and far to the left, well, it's going to get closer and closer to 0. If x minus 2 gets bigger and bigger, then the fraction 1 over x minus 2 gets smaller and smaller. In this example, we're going to have to generate the graph of a quadratic and then find its reciprocal. So the first step might be to actually graph negative x squared minus 2x plus 3. Now you can do this a bunch of ways. If you're inclined to put it in vertex form, then maybe you're going to complete the square and get it like this. I'd be inclined to factor it because I know I'm going to need x-intercepts anyways. So we have negative x plus 3, x minus 1. That tells us there are x-intercepts at negative 3 and positive 1. The vertex is halfway in between them, so that would be at negative 1. And if I want the y-coordinate, I just sub in negative 1 into this. And that's going to give me 4. So that's our basic graphing a quadratic like we did in Chapter 3. And if you need a refresher on that, check out the Chapter 3 key concepts. We also know that we've got a y-intercept of 3. Okay, so now I can graph these. If you're at a complete loss, you could make a table of values. Okay, now we're going to make the reciprocal. So the reciprocal has vertical asymptotes wherever we have x-intercepts on the original. Those vertical asymptotes in this case have equations of x equals 1 and x equals negative 3. We might notice that we have a vertex at 1, 4, negative 1, 4 rather. So when I flip that, or when I take the reciprocal of the y value, it's going to be at negative 1 and positive 1/4. It's going to be right here. The reciprocal of 0, 3 will be 0, 1/3, and so on. Invariant when y is 1 or y is negative 1. So those points are going to be on the reciprocal curve. Maybe I'll put them in blue so we can be sure which ones we know so far. Okay. The last piece of the puzzle is to figure out what's going on in the long-term behavior. So I'll just work it left to right here. Here I've got a big negative. So that's going to make for a small negative on its flip. Right here I have a small negative, so that will make for a big negative on its flip. Right here I have a small positive, so that will make for a big positive on its reciprocal. Here I have a small positive, that will make for a big positive on its reciprocal. Small negative makes for a big negative on its reciprocal. And finally, big negative makes for a small negative on the reciprocal. Now we just need to connect them up. And some of this. There we go. So there in blue is our reciprocal graph. We graphed the original. We looked for those vertical asymptotes. We took the reciprocal of some points. And then basically we just said, well, wherever it's big on the original, it's small on the reciprocal. Let's do one last one where we're asked to sketch the reciprocal on this function, which clearly has asymptotes right here. So here we're basically doing things backwards. We're given what would usually be our reciprocal graph, and we're asked to find its reciprocal. Okay, so let me do this fairly intuitively. Whatever were vertical asymptotes on the original, those are going to be x-intercepts on the reciprocal. We're just doing everything kind of in reverse. This point right here, 0, negative 1/2, that's going to turn into 0, negative 2. Okay, I'm invariant when y is negative 1 or positive 1. And in the end, we know that this is going to be big values because they were small positive values on the original. Guess what I get? That's right, a parabola. So the reciprocal of one of those weird sort of three-part looking ones is going to be one of these parabolas. That brings us to the end of our Chapter 7 material. I hope that you found this helpful, and I'll see you for Chapter 8. Take care. Bye-bye.